Something about the universe refuses to stay simple. Every generation believes it has pushed reality as far as it can go, only to discover that the horizon has quietly moved farther away. The night sky once seemed like a ceiling scattered with stars. Then it became a galaxy. That galaxy became one among hundreds of billions. Soon, the observable universe itself appeared unimaginably vast, stretching nearly 93 billion light-years across. But even that staggering scale may not represent the whole story. Hidden within the mathematics of modern physics is a possibility so extraordinary that it challenges everything humanity believes about existence. The universe surrounding us may not be the ultimate reality. Every galaxy, every black hole, every atom, and every living creature could exist inside a much greater cosmic structure beyond anything our telescopes can observe. The evidence remains incomplete, the debate continues, and the consequences of being right would redefine our place in existence forever. You're watching Starsky Science, where the universe reveals its greatest secrets. Subscribe now and join the journey. For thousands of years, humanity has looked upward searching for answers. Ancient civilizations mapped the stars with astonishing precision, believing the heavens held the blueprint of existence itself. Philosophers imagined endless skies supported by divine order, while early astronomers slowly realized that Earth was not the center of everything. Every discovery seemed revolutionary at the time, yet history has revealed a remarkable pattern. Each time we believed we had uncovered the true scale of reality, nature quietly revealed something larger waiting beyond. When astronomers first understood that the Milky Way was not the entire universe, it transformed humanity's perspective forever. Suddenly, countless distant galaxies filled the darkness. Each one contained billions of stars, many surrounded by planets that might resemble our own. The universe expanded from something enormous into something almost impossible to comprehend. Then came another surprise. Those galaxies were not standing still. During the 20th century, observations made by astronomers revealed that galaxies were moving away from one another. The farther they were, the faster they appeared to recede. This astonishing discovery led to one unavoidable conclusion. Space itself was expanding. It wasn't like galaxies exploding outward through empty space. Instead, the fabric of space stretched between them, carrying entire clusters farther apart over billions of years. It was a subtle but profound distinction, one that completely reshaped modern cosmology. Tracing this expansion backward led scientists toward an extraordinary realization. Billions of years ago, everything we observe today must have been compressed into an unimaginably dense, incredibly hot state. This became the foundation of what we now call the Big Bang Theory, not an explosion into empty space, but the rapid expansion of space itself from an extremely compact beginning. Evidence supporting this idea accumulated with remarkable consistency. One of the strongest arrived, almost by accident, in 1965. Two radio astronomers, working with a sensitive antenna, detected an annoying background signal that refused to disappear. They checked every instrument. They ruled out technical failures. They even cleaned bird droppings from inside the antenna, convinced contamination might be responsible. The signal remained. What they had unknowingly discovered was ancient light left behind from the early universe itself. Today, this faint glow is known as the cosmic microwave background, often described as the oldest light humans have ever detected. It has traveled through space for nearly 13.8 billion years, carrying with it a snapshot of the infant universe only a few 100,000 years after the Big Bang. To cosmologists, it became one of the most important pieces of evidence ever found. It confirmed that our universe had a measurable history, a beginning, an evolution, a timeline. Yet solving one mystery only uncovered another. The more accurately scientists measured the universe, the stranger it became. Galaxies were spinning far faster than expected. According to gravity, stars orbiting the outer regions of galaxies should move much more slowly. Instead, they raced around their galactic centers at astonishing speeds, behaving as though enormous amounts of invisible matter surrounded them. That unseen substance received a simple name: dark matter. No telescope has ever photographed it directly. No scientist has held a sample in a laboratory. Yet almost every observation suggests it exists. Without dark matter, galaxies would simply fly apart. Its invisible gravity appears to hold vast cosmic structures together, outweighing ordinary matter by roughly 5 to 1. Everything familiar, stars, planets, oceans, mountains, people, even every atom inside your body, accounts for only a small fraction of the universe's total matter. The realization was deeply unsettling. Most of reality appeared to be invisible. Before scientists could fully understand dark matter, another surprise emerged. In the late 1990s, astronomers studying distant exploding stars expected to measure the gradual slowing of cosmic expansion under the pull of gravity. Instead, they discovered precisely the opposite. The universe was expanding faster over time. Some unknown influence was pushing space apart with increasing strength. This mysterious effect became known as dark energy. Unlike dark matter, which exerts gravitational attraction, dark energy seems to drive the accelerated expansion of space itself. Today, it is estimated to make up nearly 70% of the total energy content of the cosmos. Think about what that means. Everything visible, the stars lighting distant galaxies, every planet, every black hole, every cloud of gas glowing across interstellar space, represents only a tiny percentage of reality. Most of existence is composed of things we cannot directly see. The universe we experience every day may be only the visible surface of something vastly deeper. As observational technology improved, researchers noticed another limitation that often goes unnoticed outside scientific circles. Even the observable universe has an edge. Not because space suddenly ends there. Not because a wall surrounds reality. The limit exists because light travels at a finite speed. Every telescope is effectively a time machine. Looking farther into space means looking farther into the past. The light from the moon reaches Earth in just over 1 second. Sunlight takes about 8 minutes. The nearest large galaxy appears as it existed millions of years ago. Some galaxies visible through the most powerful telescopes emitted their light when the universe was still in its infancy. Eventually, astronomers reach a boundary beyond which no light has had enough time to arrive since the beginning of cosmic expansion. Everything beyond that horizon remains hidden. Not necessarily non-existent. Simply unreachable. This distinction changes everything. Many people casually refer to the observable universe as though it includes all existence. It does not. It only represents the region whose light has reached us since the Big Bang. Beyond that cosmic horizon could lie vastly more space. Perhaps infinitely more. The equations of cosmology do not require the universe to end where our observations stop. In fact, several models suggest precisely the opposite. If space continues beyond our observable limit, then every galaxy we've ever detected may occupy only a tiny neighborhood within a much larger cosmos. That realization naturally raises an unsettling possibility. How large is the universe really? Scientists have searched for clues by measuring the geometry of space itself. If the universe possesses positive curvature, traveling in one direction long enough might eventually bring you back to where you started, much like circling Earth. If space has negative curvature, reality would resemble an endless saddle-shaped landscape stretching forever. If it is perfectly flat, then parallel paths continue indefinitely without ever meeting. Remarkably precise measurements of the cosmic microwave background indicate that the observable universe appears extraordinarily flat. Flatness may sound ordinary. In cosmology, it is anything but. A perfectly flat universe creates fascinating possibilities. It allows space to extend far beyond what we can observe, potentially without end. Yet another puzzle emerges. Why should the universe be so astonishingly flat at all? Even tiny deviations during its earliest moments should have grown dramatically over billions of years. Instead, the cosmos appears balanced with extraordinary precision. The odds seem almost impossibly delicate. This apparent fine-tuning troubled physicists for decades. Eventually, one idea began offering a possible explanation. An idea that would completely transform humanity's understanding of reality. It proposed that during an unimaginably tiny fraction of a second after the Big Bang, space expanded at an almost unimaginable rate. Not merely fast, faster than anyone had previously believed possible. This concept became known as cosmic inflation. At first glance, inflation solved several long-standing problems simultaneously. It explained why distant regions of the universe share nearly identical temperatures despite appearing too far apart to have ever exchanged information. It naturally accounted for the universe's remarkable flatness, and it matched observations with surprising accuracy. For many physicists, inflation became one of the most successful ideas in modern cosmology. But hidden inside its mathematics was a consequence few initially anticipated. If inflation worked the way many equations suggested, it might never truly stop everywhere. Instead, while inflation ended in one region, allowing stars, galaxies, and eventually life to form, it could continue elsewhere, endlessly generating new regions of space beyond our reach. Each newly formed region could become its own universe. Entire cosmic realms emerging like bubbles within an unimaginably larger reality. If that interpretation is correct, then our universe might not be the whole cosmos at all. It could simply be one bubble among countless others. The possibility sounds almost like science fiction, yet it emerged not from fantasy, but from attempts to solve some of cosmology's deepest puzzles. Once physicists began following the mathematics of cosmic inflation to its logical conclusion, they found themselves confronting an unsettling implication. The universe we observe might be only one tiny pocket of reality, surrounded by countless others that can never be reached. This idea is known as eternal inflation. The name is surprisingly literal. In many versions of the theory, inflation does not switch off everywhere at once. Instead, it behaves like water beginning to freeze on a winter lake. Small patches become solid while the rest remains liquid. As frozen regions expand, new ones continue forming elsewhere. Replace ice with ordinary universes, and replace the lake with an inflating sea of space, and the picture begins to emerge. Our universe could be one of those frozen regions, a place where inflation ended, allowing matter, radiation, stars, and galaxies to form. Beyond our cosmic horizon, inflation may still be creating new regions even now, forever separated from us by distances expanding faster than light can cross. It is important to understand what physicists actually mean here. Nothing is breaking Einstein's theory of relativity. Objects are not moving through space faster than light. Instead, space itself expands. Einstein's equations allow space to stretch without imposing the familiar speed limit that applies to objects traveling within it. This subtle distinction changes everything. It means entire universes could drift permanently beyond one another's reach, not because they are hidden behind walls or barriers, but because the space between them grows faster than any signal could ever travel. For observers living inside one bubble universe, every measurement would suggest they inhabit an entire cosmos. They would map galaxies, measure cosmic expansion, and build theories explaining everything they could observe. Yet beyond their horizon, an unimaginably larger reality could remain forever invisible. That sounds strangely familiar. It mirrors our own situation almost perfectly. Everything we know about the universe comes from information carried by light, gravity, or other particles that have reached us. We cannot observe what lies beyond our cosmic horizon because no information from those regions has had enough time to arrive since the universe began expanding. This limitation creates one of science's greatest philosophical challenges. How do you investigate something that may exist forever beyond observation? Normally, scientific ideas are tested through experiments or direct observations. Eternal inflation appears to resist both. Critics argue that a theory describing permanently unobservable regions risks crossing the line between physics and philosophy. Supporters respond differently. They point out that many scientific discoveries began as mathematical predictions long before observations confirmed them. Black holes were once dismissed as bizarre solutions hidden inside Einstein's equations. Gravitational waves existed only on paper for a century before detectors finally measured them. Even the Higgs boson was predicted decades before experiments at the Large Hadron Collider confirmed its existence. History teaches an important lesson. Sometimes mathematics sees reality before telescopes do. That possibility keeps eternal inflation alive within serious scientific discussions. Yet inflation is only one path leading toward the idea that our universe could exist inside something much larger. Another path begins with one of physics' oldest ambitions, the search for a theory of everything. Modern physics rests upon two extraordinary achievements. The first is quantum mechanics, which describes the bizarre behavior of particles at unimaginably small scales. It explains atoms, electrons, light, and the strange probabilities governing the microscopic world with astonishing precision. The second is Einstein's general theory of relativity, which explains gravity as the curvature of space and time. It successfully predicts planetary motion, black holes, gravitational lensing, and even the expansion of the universe itself. Separately, these theories work remarkably well. Together, they refuse to cooperate. Whenever scientists attempt to combine quantum mechanics with general relativity under extreme conditions, such as inside black holes or during the universe's earliest moments, the equations become unstable. Infinite values appear where meaningful answers should exist. Nature almost seems to be telling physicists that something fundamental is missing. That missing piece has inspired decades of research. One of the most ambitious candidates is string theory. Unlike traditional physics, which treats elementary particles as point-like objects, string theory proposes that the smallest building blocks of reality are unimaginably tiny vibrating strings. Different patterns of vibration create different particles. One vibration appears as an electron. Another behaves like a quark. Another could represent particles responsible for forces themselves. The elegance of the idea attracted enormous attention because it naturally includes gravity while remaining compatible with quantum mechanics. But it introduced an unexpected complication. The mathematics only works if reality contains more dimensions than we experience. Not 4 dimensions, 3 of space and 1 of time. 10, sometimes 11. At first glance, this seems absurd. Where are these hidden dimensions? Physicists suggest they may be curled into unimaginably tiny shapes at every point in space, far too small for current instruments to detect. Like a garden hose viewed from a great distance, it appears as a simple line. Only when examined closely does its circular thickness become visible. If extra dimensions exist, they may influence reality without being directly visible. And once extra dimensions become part of the picture, astonishing new possibilities begin to appear. Some versions of string theory describe our entire universe as existing on an enormous 3-dimensional membrane called a brane, floating within a higher dimensional space, often called the bulk. Everything familiar, light, atoms, planets, galaxies, would remain trapped on our cosmic membrane. Gravity, however, might spread into the higher dimensional bulk. That idea could explain why gravity is so much weaker than the other fundamental forces. Perhaps much of its strength leaks into dimensions beyond our perception. Even more remarkably, if multiple branes exist within this higher dimensional space, then our universe might have neighbors. Entire universes could drift alongside ours, separated by distances measured not across ordinary space, but across dimensions we cannot directly perceive. To visualize this, imagine two sheets of paper stacked together. Tiny creatures living on one sheet would know only length and width. They could travel in every direction available to them, yet never leave the surface. The second sheet would remain completely invisible. Not because it is far away, because it exists in a direction the creatures cannot access. If reality contains higher dimensions, our own universe could resemble one of those sheets. Other universes might exist astonishingly close, while remaining forever inaccessible. This concept inspired one of the boldest cosmological proposals ever developed. According to the ekpyrotic universe model, the Big Bang may not have been the true beginning of everything. Instead, it could have resulted from a collision. Imagine two immense cosmic brains drifting through higher dimensional space over unimaginable stretches of time. Eventually, they collide. The impact releases extraordinary energy. To observers living inside one brain, that event would appear exactly like a Big Bang. The universe begins. Matter forms. Expansion starts. Time, as we measure it, unfolds. Yet from the higher dimensional perspective, it was simply two larger structures meeting. The implications are astonishing. Our universe would not represent the birth of all existence. It would merely mark one event inside a far greater cosmic environment. Some versions of this idea even suggest such collisions happen repeatedly over unimaginable timescales, creating cycles of cosmic birth separated by trillions upon trillions of years. Although these models remain speculative, they demonstrate something remarkable. Completely different areas of theoretical physics continue pointing toward larger realities beyond our observable universe. Not because scientists are trying to invent mysterious worlds, because the mathematics keeps opening unexpected doors. Of course, extraordinary claims demand extraordinary evidence. Can any of these ideas actually be tested? Researchers have searched for subtle fingerprints that neighboring universes might leave behind. One possibility involves the cosmic microwave background, the ancient light released shortly after the Big Bang. If another bubble universe collided with ours in the distant past, the impact might have left faint circular patterns or unusual temperature variations imprinted across this ancient radiation. Over the past 2 decades, scientists have carefully examined increasingly detailed maps produced by satellites like WMAP and later the European Space Agency's Planck mission. Several intriguing features attracted attention. One became famous as the cold spot, an unusually large region appearing slightly cooler than surrounding areas. Some researchers briefly wondered whether it could represent evidence of an ancient collision between universes. The idea captured headlines worldwide. Yet science demands caution. Subsequent studies suggested more conventional explanations remain entirely possible, including enormous cosmic voids affecting the light traveling toward Earth. Today, no convincing evidence confirms that the cold spot resulted from another universe. It remains an interesting anomaly rather than proof. That distinction matters enormously. In science, unanswered questions are not evidence by themselves. Mysteries invite investigation. They do not automatically validate extraordinary conclusions. Still, physicists continue searching because future observations may reveal patterns impossible to explain through known processes alone. Upcoming observatories promise even greater precision. New generations of telescopes will map billions of galaxies, measure subtle distortions in spacetime, and study the universe with unprecedented sensitivity. Every improvement increases the possibility of finding clues hidden within the cosmos itself. Yet another mystery has begun attracting attention for an entirely different reason. It concerns black holes. For decades, black holes were viewed as cosmic endpoints, places where matter disappears and known physics breaks down. Today, many physicists suspect they may be hiding something far stranger. Something that, if true, could completely transform the question we began with. Because under certain extraordinary ideas, a black hole may not simply destroy a universe. It may create one. Black holes have always occupied a strange place in physics. They are among the simplest objects described by Einstein's equations, yet they contain some of the deepest mysteries in science. From a distance, they appear almost ordinary. A black hole can be completely described by just a few properties: its mass, its electric charge, and its spin. But behind its event horizon, where no information can escape back into the outside universe, the familiar rules governing space and time begin to unravel. For decades, physicists believed that anything crossing the event horizon was destined to fall toward a single point of infinite density known as a singularity. A singularity represents more than an extremely dense object. It marks the place where our current understanding of physics simply stops working. General relativity predicts infinite curvature, infinite density, and conditions where the equations themselves lose their meaning. Whenever infinities appear in physics, they usually signal that an incomplete theory has reached its limits. Nature rarely produces true infinities. Instead, they often indicate that something deeper remains undiscovered. This realization has led many physicists to believe that singularities may not actually exist in the form Einstein's equations predict. Somewhere before infinite density is reached, quantum effects, the strange rules governing the smallest scales of reality, are expected to take over. Unfortunately, no complete theory of quantum gravity yet exists. Without it, scientists can only explore possibilities. Some of those possibilities are astonishing. One idea suggests that the crushing force inside a black hole might eventually halt before reaching infinity. Instead of collapsing forever, space itself could undergo a dramatic transformation. Rather than ending, it could begin expanding again. Not outward into our universe, outward into a completely new one. This concept first emerged from attempts to combine quantum mechanics with cosmology. Several researchers noticed that under certain mathematical conditions, gravitational collapse and cosmic expansion resemble opposite sides of the same process. Think about the Big Bang for a moment. Modern cosmology describes the early universe as an incredibly hot, incredibly dense state that expanded rapidly into the vast cosmos we observe today. Now compare that picture with the interior of a collapsing black hole. Matter falls inward. Density increases dramatically. Space becomes extraordinarily compressed. At first glance, these seem like opposite events. But some theoretical models suggest they could be connected through physics we do not yet fully understand. Instead of matter being crushed into an impossible singularity, the collapse might bounce, triggering expansion on the other side. To observers inside that expanding region, it would appear exactly like the birth of an entirely new universe. Its own space, its own time, its own galaxies, its own future. Meanwhile, from the outside, the parent black hole would simply continue existing as another black hole. Neither civilization would be aware of the other. The event horizon would permanently separate their realities. It is an extraordinary idea, but it raises an even more extraordinary question. If black holes can create universes, could our own universe have begun inside one? Several respected physicists have explored variations of this possibility over the years. While no version has been confirmed, the hypothesis offers intriguing solutions to some long-standing puzzles. One puzzle concerns the remarkable uniformity of the early universe. Another involves the mysterious arrow of time. Why does time appear to move in only one direction? Why do we remember the past, but never the future? Inside a newly forming universe emerging from gravitational collapse, time would naturally point away from its beginning, just as it does in our own cosmos. The connection is far from proven, but it demonstrates how deeply cosmology and black hole physics may be intertwined. Then there is another fascinating implication. Every massive black hole in our universe could potentially give birth to another universe. Each of those universes could eventually produce countless stars. Some stars would collapse into new black holes. Those black holes might generate even more universes. The process could continue indefinitely, forming an immense cosmic family tree stretching across realities we can never directly observe. This idea became especially interesting when physicist Lee Smolin proposed a hypothesis known as cosmological natural selection. The inspiration came from biology. In biological evolution, organisms reproduce with small variations. Those best suited to their environment leave more descendants. Smolin wondered whether universes might behave in a surprisingly similar way. Suppose each new universe inherits physical laws almost identical to its parent, but with tiny random changes in fundamental constants. Most combinations would create sterile universes where stars never form. Others might collapse almost immediately. Some might expand too rapidly for galaxies to develop. But a small number would efficiently produce enormous numbers of massive stars. Those stars would later collapse into black holes. If black holes create new universes, then universes producing more black holes would naturally generate more offspring. Over unimaginable timescales, universes capable of creating abundant black holes would become increasingly common. Remarkably, our universe appears extremely efficient at producing stars. Whether that observation supports Smolin's idea remains uncertain, but it offers an elegant example of how evolutionary thinking might extend far beyond biology. Even if cosmological natural selection eventually proves incorrect, it illustrates an important principle in modern theoretical physics. Scientists are not inventing strange possibilities simply to make reality more mysterious. They are following mathematics and physical laws wherever those paths lead, even when the destination seems almost unbelievable. Yet black holes are not the only places where reality begins behaving in unexpected ways. Quantum mechanics introduces mysteries every bit as profound. At the microscopic scale, particles refuse to behave like tiny solid objects. Electrons can exist in overlapping probabilities. Photons behave as both particles and waves. Two particles can become entangled so completely that measuring one instantly determines the state of the other, regardless of the distance separating them. Albert Einstein famously disliked this implication, calling it spooky action at a distance. Decades of increasingly sophisticated experiments have shown that quantum entanglement is real. It does not allow faster-than-light communication, but it demonstrates that reality possesses connections unlike anything found in everyday experience. Some physicists now suspect that quantum entanglement may play an even deeper role. Perhaps spacetime itself emerges from networks of quantum information. If true, space would not be fundamental. It would be built from something more basic. This possibility has transformed several areas of theoretical physics over the past decade. One particularly intriguing idea comes from the surprising relationship between entanglement and wormholes. A wormhole is a hypothetical shortcut connecting distant regions of spacetime. Although none has ever been observed, Einstein's equations allow such structures under certain conditions. More recently, physicists Juan Maldacena and Leonard Susskind proposed a bold conjecture summarized by an unusual phrase: ER equals EPR. The name combines two famous concepts. ER refers to Einstein-Rosen bridges, another name for wormholes. EPR refers to the famous Einstein-Podolsky-Rosen thought experiment involving quantum entanglement. Their proposal suggests that entangled particles and microscopic wormholes might actually represent two different descriptions of the same underlying reality. If correct, the universe may be woven together through relationships far more intricate than ordinary geometry suggests. Distance itself might not be as fundamental as it appears. Although this idea remains highly theoretical, it demonstrates how modern physics increasingly blurs distinctions once considered absolute. Space, time, information, gravity, quantum mechanics. Instead of separate subjects, they may all emerge from a deeper framework we have only begun to glimpse. And that brings us back to the question at the heart of this documentary. Is our universe inside another universe? By now, the possibility no longer sounds quite as impossible as it did at the beginning. Inflation points toward ever-growing cosmic bubbles. String theory introduces higher dimensional realities. Black hole cosmology suggests universes giving birth to universes. Quantum gravity hints that spacetime itself may emerge from something even more fundamental. Each idea approaches the mystery from a different direction. None has been proven, yet none can be casually dismissed either. Science often advances in unexpected ways. History is filled with ideas that once seemed outrageous before evidence transformed them into accepted knowledge. Continents drifting across Earth, invisible atoms composing matter, expanding space, black holes, gravitational waves. Every one of these concepts was initially met with skepticism. The difference, of course, is that they eventually accumulated overwhelming observational support. The great challenge facing modern cosmology is determining whether the same will ever happen for theories describing realities beyond our own. Future generations may possess instruments capable of detecting subtle signatures we cannot yet measure. Entirely new branches of physics may emerge. Or researchers may discover that today's boldest ideas require fundamental revision. Either outcome would deepen our understanding of existence. Because every serious attempt to answer this mystery pushes science toward a more complete picture of reality. And recently, an entirely different line of research has begun challenging one of our oldest assumptions, not about where the universe exists, but about what the universe actually is. Some physicists now wonder whether space, time, and even gravity are not the foundation of reality at all, but the visible result of something far more fundamental, a possibility that could redefine the meaning of existence itself. For centuries, scientists searched for the smallest building blocks of reality. First came molecules, then atoms, then electrons, protons, neutrons, quarks, and an expanding family of elementary particles. Each discovery peeled back another layer of nature, revealing a world more intricate than anyone had imagined. Yet modern physics is beginning to ask a radically different question. Perhaps particles are not the true foundation of reality. Perhaps even space and time themselves are not fundamental. Instead, they may emerge from something deeper, something that does not resemble matter or energy at all. This shift in thinking has become one of the most exciting frontiers in theoretical physics. It is driven by an unexpected realization. Whenever physicists attempt to describe black holes, quantum mechanics, and gravity together, information keeps appearing at the center of the story. Not matter, not energy, information. The idea sounds abstract at first, but information has a precise meaning in physics. Every particle carries measurable properties. Every interaction changes those properties in predictable ways. The universe constantly stores, transforms, and transfers information. Then came one of the greatest paradoxes in modern science. In the 1970s, Stephen Hawking showed that black holes are not completely black. Quantum effects near the event horizon allow them to emit an incredibly faint glow now known as Hawking radiation. Given enough time, a black hole slowly loses mass. Eventually, it disappears. That prediction created a profound problem. If everything falling into a black hole is destroyed when the black hole evaporates, then the information describing those objects would vanish forever. Quantum mechanics says that cannot happen. Information must always be preserved. General relativity appeared to say otherwise. Two of physics' greatest theories suddenly contradicted one another. For decades, this became known as the black hole information paradox. Some of the world's brightest physicists have devoted entire careers to solving it. While no universally accepted solution exists, one proposal has changed how scientists think about reality itself. It became known as the holographic principle. At first, the name sounds almost mystical. In reality, it comes directly from black hole mathematics. Researchers discovered something extraordinary while calculating black hole entropy, a measure of information. Normally, you would expect information to increase with volume. A larger box holds more information than a smaller one. Black holes behave differently. Their information appears to scale with surface area instead. That subtle mathematical result inspired an astonishing possibility. Perhaps our familiar three-dimensional universe behaves similarly. Maybe everything occurring inside a region of space can be completely described by information encoded on its boundary. If true, the universe would resemble a hologram, not a fake illusion. A fully real three-dimensional world emerging from deeper two-dimensional information. Although this idea remains highly theoretical, it has become one of the most influential concepts in modern physics because it successfully appears within several advanced mathematical frameworks, particularly those connecting gravity with quantum mechanics. Imagine reading a novel. Every character, every city, every conversation exists because of patterns of ink arranged on flat pages. The pages themselves are two-dimensional, yet an entire world emerges in your mind. The holographic principle suggests something equally surprising may occur in nature. Our three-dimensional universe could emerge from information existing on a deeper boundary we cannot directly perceive. If that sounds unbelievable, consider how often reality has overturned common sense before. Earth feels motionless. It is racing around the sun. Solid objects feel continuous. They are mostly empty space. Time feels universal. Einstein showed that it depends on motion and gravity. Again and again, the universe has refused to match human intuition. Perhaps our intuition about dimensions is simply the next assumption waiting to be challenged. The deeper physicists explore quantum gravity, the more often information appears to take priority over geometry itself. Some researchers now argue that spacetime is not the stage on which physics happens. Instead, spacetime may emerge from networks of quantum relationships. In other words, geometry could be a consequence rather than a cause. This represents one of the biggest conceptual shifts since Einstein introduced general relativity. If correct, asking whether our universe exists inside another universe may be similar to asking whether one chapter exists inside an entire book. The chapter is completely real. Its characters experience genuine events. Yet the larger structure containing it operates according to rules they cannot perceive from within. That comparison, while imperfect, captures the challenge facing cosmologists. We are attempting to understand the container while living entirely inside its contents. Every experiment, every telescope, every equation, everything we know comes from within our own observable universe. Trying to infer what lies beyond is like studying the ocean while never leaving a single island. Even so, humanity has repeatedly succeeded in uncovering realities far beyond direct experience. No one has traveled to the center of the sun. Yet physics accurately predicts the nuclear reactions powering it. No one has visited the earliest moments after the Big Bang. Yet observations of the cosmic microwave background allow scientists to reconstruct those ancient conditions with remarkable precision. Science advances by connecting evidence through mathematical consistency. That is precisely why theories about larger cosmic structures remain scientifically interesting, despite the absence of direct confirmation. Still, there is an important distinction that deserves emphasis. A fascinating idea is not automatically a correct one. Some popular discussions blur the line between established science and speculation. They present every hypothesis as though it were equally supported. Professional physicists do the opposite. They rank ideas according to evidence. The expanding universe is supported by overwhelming observations. The cosmic microwave background has been measured with extraordinary accuracy. Dark matter has compelling indirect evidence, even though its exact nature remains unknown. Cosmic inflation is strongly supported by several observations, but is still being refined. Eternal inflation, higher dimensional brains, universe-producing black holes, and holographic cosmology remain active areas of theoretical research without definitive experimental confirmation. Recognizing those differences is essential. Science grows stronger by acknowledging uncertainty rather than hiding it. Ironically, uncertainty is often where the greatest discoveries begin. History offers remarkable examples. When astronomers noticed tiny irregularities in the orbit of Uranus, they did not dismiss them. They predicted another unseen planet. Eventually, Neptune was discovered almost exactly where mathematics suggested. When Mercury's orbit refused to match Newton's laws, scientists searched for explanations. The answer eventually emerged through Einstein's general relativity. Today, cosmologists face irregularities of a different kind. Dark matter, dark energy, quantum gravity, the origin of spacetime, the true size of reality. These mysteries may eventually point toward entirely new physics, just as earlier puzzles transformed our understanding of the cosmos. And perhaps the most humbling lesson is this: every major scientific revolution has reduced humanity's sense of central importance. We once believed Earth stood at the center of creation. Then we learned it orbits an ordinary star. We believed the Milky Way contained everything. Then we discovered hundreds of billions of other galaxies. We assumed visible matter dominated reality. Now we know it represents only a small fraction of the universe. Each discovery expanded the scale of existence while shrinking the boundaries of certainty. If our universe truly exists within a greater cosmic structure, it would continue that pattern. Not by making humanity insignificant, but by revealing that reality is richer than we ever imagined. Whether that larger structure contains dozens of universes, infinitely many, higher dimensions, or something no current theory has predicted, one fact remains constant. The universe has repeatedly proven more creative than human imagination. Every time scientists believed they had reached the final layer of understanding, nature quietly revealed another. Perhaps that process will never end. Perhaps every answer opens the door to an even deeper question. And if that is true, then the mystery we began with is not simply about where our universe exists. It is about whether there is any ultimate boundary to knowledge at all. Today, powerful observatories are mapping billions of galaxies. Gravitational wave detectors are listening to collisions between black holes across the cosmos. Particle accelerators continue probing nature at unprecedented energies. Each new observation has the potential to eliminate old theories or uncover clues pointing toward realities no human has ever conceived. Somewhere within that growing mountain of data may lie the first genuine evidence that our universe is part of something far greater. Or perhaps the evidence will lead somewhere even stranger. Because one possibility remains that is arguably more astonishing than all the others. It suggests that the universe is not merely contained within a larger cosmos. It suggests that reality itself may have no final level at all. The idea that reality might have no final level is difficult to grasp because human intuition has always searched for endings. We expect every road to reach a destination, every story to conclude, and every mystery to have a final answer waiting at the end. But the universe has rarely behaved according to those expectations. Every major scientific breakthrough has revealed that nature is more layered than anyone imagined before it. Ancient astronomers believed the stars were fixed lights attached to a celestial sphere. Centuries later, telescopes showed that those stars were distant suns. Then those suns became members of galaxies. Galaxies became part of clusters. Clusters became threads within enormous cosmic webs, stretching across billions of light years. Even today, the largest structures in the observable universe continue challenging our understanding of how matter organizes itself across unimaginable distances. At every stage, humanity thought it had reached the biggest picture. At every stage, the picture grew larger. That historical pattern makes one question increasingly difficult to ignore. What if our observable universe is simply another step in that endless progression? Not the final level, not the complete reality, just another layer waiting to be placed inside an even greater one. Modern cosmology cannot yet answer that question. But remarkably, neither can it dismiss it. Some scientists have suggested that reality could be fundamentally hierarchical. Universes might exist inside larger universes, which themselves exist inside structures of even greater scale. Each level would obey physical laws that appear complete to observers living within it, while remaining only a small component of something beyond their perception. The idea resembles Russian nesting dolls, where every doll fits inside a larger one. The comparison is useful, but reality, if this picture is correct, would be far stranger. Unlike wooden dolls, each universe could possess different physical constants, different amounts of dark matter, different strengths for gravity, different numbers of spatial dimensions. Some might never form stars. Others could collapse almost immediately after their birth. Some might expand so rapidly that galaxies never have time to emerge. Only a small fraction might develop the complex chemistry required for planets, oceans, and eventually life. That possibility naturally connects to another mystery that has fascinated physicists for decades. Why does our universe seem so remarkably suited for complexity? Gravity is neither too strong nor too weak. The electromagnetic force allows stable atoms to exist. Nuclear forces permit stars to shine for billions of years. The masses of fundamental particles fall within astonishingly narrow ranges that allow chemistry to function. Even tiny changes in several of these values would produce a universe dramatically different from our own. This observation has become known as the fine-tuning problem. Some researchers argue that fine-tuning points toward undiscovered physical principles that uniquely determine the constants of nature. Others propose the multiverse. If countless universes exist, each with different physical properties, then it is hardly surprising that at least a few possess conditions allowing observers to emerge. After all, only those observers living in such universes would ever ask why their cosmos appears suitable for life. This reasoning is known as the anthropic principle. It remains controversial because it explains observations statistically rather than predicting new physical laws. Even so, it continues to influence discussions surrounding cosmology, inflation, and string theory. Yet perhaps the most important lesson is not whether the multiverse ultimately proves correct. It is how science approaches questions that currently lie beyond direct observation. Contrary to popular belief, scientists are not free to invent unlimited possibilities. Every serious hypothesis must remain consistent with established evidence. It must agree with successful observations. It must survive mathematical scrutiny. And ideally, it should make predictions that future experiments could test. That disciplined approach is what separates science from speculation. When physicists discuss eternal inflation, higher dimensional brains, holographic spacetime, or universes emerging from black holes, they do so because these ideas arise naturally from attempts to solve real scientific problems. They are not conclusions. They are possibilities. Some will almost certainly be proven wrong. Others may evolve into entirely different theories. A few might eventually reshape civilizations' understanding of existence. History offers every reason to remain humble. Few people living in the 19th century could have imagined quantum mechanics. Few scientists at the beginning of the 20th century expected space itself to expand. Even fewer predicted that invisible dark matter and dark energy would dominate the universe. Each revolutionary discovery forced humanity to rewrite its understanding of reality. There is every reason to believe that future generations will rewrite ours. The next breakthrough may come from a telescope orbiting far beyond Earth. It may emerge from a gravitational wave detector, listening to ancient collisions across the cosmos. It may arise inside a particle accelerator, probing energies never before achieved. Or perhaps it will begin with an unexpected equation scribbled across a notebook by a physicist trying to solve a problem that initially appears unrelated. That is often how science advances. Not in straight lines, but through surprising connections between ideas that once seemed completely separate. The search to understand whether our universe exists inside another universe has already accomplished something extraordinary. It has united cosmology, quantum mechanics, black hole physics, information theory, relativity, and particle physics into one of the greatest scientific investigations ever undertaken. Whether the final answer turns out to be yes, no, or something entirely unforeseen, the journey itself is expanding humanity's understanding of the cosmos. Perhaps that is the deepest lesson hidden within this mystery. The universe is not obligated to match human expectations. Reality is under no obligation to be simple. Every generation inherits a map of the unknown. Every generation pushes that map a little farther into the darkness. Our ancestors crossed oceans, believing they had reached the edge of the world. Instead, they discovered continents. Astronomers pointed telescopes toward faint patches of light, expecting distant stars. Instead, they found galaxies. Physicists searched for the smallest particles. Instead, they uncovered a quantum world, unlike anything visible in everyday life. Today, scientists are asking whether our entire universe is merely one region within an even greater reality. Whether that question ultimately transforms into accepted science or remains one of history's most fascinating hypotheses, it reminds us of something profoundly important. Curiosity has always been humanity's greatest instrument. Every equation begins with a question. Every telescope begins with curiosity. Every discovery starts with the willingness to admit that we do not yet know the full story. Somewhere beyond the reach of today's instruments, beyond the observable horizon, beyond the limits of our current theories, answers may already exist. Or perhaps those answers will reveal even deeper mysteries waiting beyond them. If the history of science teaches us anything, it is this. The universe is almost always stranger than our first explanation, and often far more beautiful than our boldest imagination. One day, humanity may finally discover whether our universe is the whole of reality, or just one chapter in a far grander cosmic story. Until then, the greatest frontier is not merely the universe above us. It is the endless pursuit of understanding itself. If you enjoyed this journey through one of cosmology's greatest mysteries, like, share, and subscribe to Starsky Science for more mind-expanding science documentaries.